Hello everybody, it's old Shazizz here. This is a video I'm going to call How Far To. If you watched my last video, you get a general idea of what I'm doing here. But for those that didn't see the last one, basically what I've got going on here in this big old cluster of wires and such, I've got a DDS signal generator that, excuse me, let me see if I can take you on a tour here. It's going to be shaky, sorry. Let's see if I can get that in there. Alright, so it's kind of blurry, but at 600 hertz square wave, pulsing a DDS signal generator. If you look right here, that's a USB charger coming out of the wall outlet there that is running this DDS signal generator. So you can look up this particular model here on the internet and you can find out all the specific voltages and such. But essentially it's a 5-volt input into this DDS signal generator, and then without being under a load, this thing will put a around 9-volt output. And so with that said, I'm pulsing a 600 hertz square wave through a capacitor and a microwave oven transformer, and then from that point on, let me get this little motor out of the way. From that point on, pulsing the secondary. If you see up here on the top, hopefully you can see that, those are the specs of the actual microwave oven transformer normally. I got a hole drilled in there with a screw for the ground portion of the high voltage side. So anyway, it's ramping that voltage up and then running through that capacitor and that capacitor, both in series, one with each leg of the output of the secondary. Then I'm taking that into a bridge rectifier. It's about 1,000 volt, let's see, 1,000 volt 100 amp bridge rectifier. And from that point on, going out, once it's rectified into DC current, going out into a DC capacitor, and then down into a smaller DC capacitor. This LED is not hooked up at the moment. And from that point, I have in series with the two negative rails, the negative side of the capacitor and the negative side of the bridge rectifier, I have these two 500,000 microfarad audio capacitors that are right now setting at 5.32 volts. Let's see. Sorry. Alright. So, also, I have down here a 7.2 volt nickel cadmium battery setting at 5.32 volts. And keep in mind that this nickel cadmium battery, when I started, would not hold a charge. As well as I have right here one 9-volt battery and one 9-volt battery there in series with this particular capacitor right here. This audio car capacitor. And so this battery and that capacitor is all making a loop like this. And right now they're maintaining at 4.32 volts. So eventually these will probably balance themselves down. But either way, this battery right here was not a good battery, and that battery right there was not a good battery. But right now, between that system there, they're maintaining at 4.32 volts. So from that point, off of this capacitor right here, I have the outputs going into this little boost converter circuit, which is going into this 9-volt circuit right here. Now when that 9-volt circuit's completely charged up, that blinking blue LED will be on, and that blinking red and that blinking red LED will be on. Right now I'm setting at 7.7 volts on the output of that bridge rectifier, the capacitors, this circuit, while all this is under a load. So some of you might not understand what it is that I'm trying to show you here at this moment, but it all makes sense here pretty soon. Let me get this camera stabilized. Sorry about that. Alright, so I want to see how far that I can actually push the voltage while pulsing a signal generator. Right now, like I said, I'm at 600 hertz with a square wave, and you can see that everything that's in that circuit right there would actually be considered as a load. Each one of those batteries as they're charging, and the capacitors as they're charging, the transformer, any resistance that it would have met from the time it comes out of that signal generator, pulsing that transformer, and where it finally ends up stabilizing the voltage at. Now slowly I'm getting a little bit of a decrease on the batteries as they start to match up where that capacitor level is at. And so when I finally get down to the actual final voltages, I'll document that and let you know what all the final voltages are going to be. But this goes, I've actually been running this thing since yesterday, early in the morning, about the same time as today. So it's been running for quite some time, and it's been running off of that right there, and then you will see the voltage go up, circuits come on, and then when the voltage drops, circuits go down, and then when the voltage gets back up once again, circuits coming back on. But either way, if you actually do the calculations of what that USB transformer is actually capable of, and I don't have the specs on it right now. I used to have it for the other DDS signal generator that I burnt up. But the whole key of this thing is to see what is the maximum amount of efficiency that I can get out of the output voltage coming off of that, which essentially ends up being whatever the output voltage is that that USB charger up there and that surge protector will be able to push out. So right now my voltages are at 7.77 volts from the output of that bridge rectifier while everything is under a load, and my capacitors and the circuits are fluctuating between 5.32 volts and 5.31. Looks like that, I can't tell if it's going up or down just yet, but it'll get around about 4 something when everything balances itself out, and the voltage on the output will level off around about anywhere from 7.06 to 7.10 or 710, and they will fluctuate up and down as long as that thing is running. So the maximum amount, being conservative, if I take the lowest one down there, let's see, let's just go to 7.4 volts right there. That's giving it some extra there. So 5 volts output to the signal generator, pulsing 600 hertz of square wave, pulsing a microwave oven transformer, which in turn is running the high voltage secondary off of the transformer, ramping the voltage up, running it through 2 AC run capacitors, down into a bridge rectifier, over into a DC capacitor with, get that in the picture down there. This nickel cadmium battery right here, right in series with the 2 negative rails of the output of the bridge rectifier and the input of the DC capacitor. So this is running in series with that. So it's basically completing the circuit. So a little bit of energy is actually being stuck into that battery as it flows right on by. And the same concept is for these 2 car audio stereo amplifier capacitors, 500 it's 500K, 500,000 farad microfarad capacitors, which are run in series with the 2 negative of the bridge rectifier on the output and the negative of the DC capacitor on the input of that side. These 2 nickel metal hydride batteries that I showed you, the 9 volt batteries, which both had really low voltage when I started, they're rechargeable nickel metal hydride, just like the rechargeable nickel cadmium battery down there, and they're running series with each other and this capacitor right here. So it's making a loop. Alright, so the only thing going on right now here is it's charging out, and it's going to find a level off spot. Once it finds that level off spot and I have all the numbers, I'm going to continue to add to this series of how far that I can push efficiency. And then once I have a leveled out spot where I know where I can actually run a real-time load, then we can do some measurements as far as the math goes and see where we stand at that point. But from 5 volts output, I'm personally impressed with the fact that from that 5 volts output from that USB charger, from my understanding of how this circuitry inside that DDS signal generator functions, that without being under a load, it'll push out about a 9 volt output. And once again, keep in mind, folks, I'm only interested in voltage. I'm not interested in all the rest of the stuff, and it'll become apparent why when it's all said and done. Basically, all of these capacitors are being pressurized, and that's a terminology that anybody who's into electronics or electrical engineer probably doesn't like to hear, but that's my my view on what's going on here. It's like this balloon in the bottle that I did call in the physics toy. Go watch my video physics toy. It's pretty neat how this thing basically explains kind of like how a capacitor actually works. But with my understanding of how that signal generator works, and that I'm pushing 600 hertz square wave to a transformer and running all of this stuff off of that 5-volt output, and coming up with everything that's on here is a surplus voltage. 7.76, 5.31, and 5.31 until this thing levels out, until all the power is out of those batteries, until it finally finds its perfect balance in there and the final voltages come in. Now, before I added that into the circuit, the 9-volt on this side, I actually had this little electric motor running in series with that instead of that. And I'm going to go ahead and take this battery out of the equation for the moment, and I'm going to put this little electric motor, which is not going to run, but it is going to complete the circuit. And it should start dropping down the voltage. Yeah, don't want them wires touching each other. Stop it. Alright. Okay, so now that little electric motor is actually ran in series with that battery over there, and whenever the pressure on that side gets high enough, it will actually run that electric motor. So it's almost acting like a low voltage circuit, that whenever the battery gets to a low voltage, it actually disconnect the load, and then when the battery gets high enough, it'll actually reconnect the load. So you can see my voltage is going down, and it will finally get to the point where it will level off, and that motor will not even affect the circuit anymore until that battery gets charged up, until that one of these circuits right here finally drains it back down, and eventually you'll have just this one here blinking, and the voltage will fluctuate from 7.04 and around about 4 volts on this side over here, 4.60 I think it was when it was leveled out. When it finally levels out, that will be at 7.04, and this will be at 4.60, and then it will fluctuate up. It'll charge up, and then it'll bring itself back down, and whatever demand that this particular circuit inside of this one right here makes, that will be the draw right there that draws the power down. And when it gets charged back up, where that circuit will be able to run right, so you can see this one over here starting to blink down. So the maximum so far, while it's under a load, is running that circuit, putting a slow charge to that battery down there, and a slow charge to this battery right here. When it gets up to a certain extent, that capacitor right there, the circuit inside that capacitor is draining off a little bit at a time until it slowly gets down, and it'll level out to 704. It'll work its way up to about 7.10, and then back down to 704, and then back up to 710. So for the moment, I'm going to take this little electric motor back out of here and put this back in series. Notice that I got my positive on my negative and my negative on my positive. So those are ran in series. And you can see the voltage rising again. So at some point that's going to find a balance. And whereas these batteries right here, while running an actual load, will go down, the energy is being transferred back and forth to that capacitor, to these batteries. As long as that 5 volts is coming in and coming down through this right here, if I can maintain the voltage that is coming out of that USB charger to whatever the voltage is, and even the current from that side over there, because once it comes out of that signal generator, we're not talking about current anymore. We're just ramping it up to voltage alone, and we're using the voltage to pressurize the capacitors, which is charging all the loads, including these batteries. I got 7.66 over here, I got 5.21 there, and 5.21 there. I'm going to be replacing a couple of the capacitors in there with supercapacitors because they work a lot better for storing quite a bit of power. Actually, you've seen some videos out there where they've actually used these to start cars with. They made little capacitor banks and started cars with them. But if you understand what it is that I'm showing you here, and before all my critics hit me and try to start giving me a rash, I don't know what I'm talking about. I know exactly there is a method to my madness, and when you see what it is that I'm trying to show you as far as how efficiency is and the results that come out of this particular experiment, I think you're going to be very pleased. It doesn't take near the amount of power to run the things that we run. There's a whole lot of losses in this system. And this microwave oven transformer, which normally requires a lot of current to put out the voltage that it does. Now keep in mind, I'm more than likely not getting near the amount of voltage out because I'm only pulsing at 600 hertz with a square wave, starting with an input of 5 volts. But this transformer's cold. That bridge rectifier's cold. Everything's staying cool. And the only reason why a transistor or resistor or any of the electrical components ever fail is because they get hot from too much current. They meet their too much resistance, they get hot, and they fail. They reach their thermal breakdown. And so if you can transfer energy from one place to the next and do it in the coolest fashion possible, you just increased your efficiency and the lifespan of your electronics, or even your electrical motors for that matter. But so I'm on my second day of running this signal generator, and these are the measurements so far. So before all my critics give me a rash about, well, you know, I can't run my house on that, and that's not free energy and all that kind of craziness, don't even bother. It's ridiculousness. Because when you see what it is that I'm talking about, and we push the limits of efficiency, everything that I've told you about is going to make perfect sense. And if you start engineering some equipment, you can get the maximum, I mean the maximum amount of power that your generators are capable of producing. You will be able to transfer that energy without all the losses that you did prior. And of course, every single time I say something remotely like that, somebody's always going to say, oh, well, there's always losses in time you move energy. There are only losses if you do not capitalize on those what would have been losses and move that energy forward. That's including heat. And so if you can move everything that would have been a loss into a storage bank of some sort, then you have no losses in the system. They say energy can neither be created nor destroyed. So where does it go? Some of it gets lost via heat, friction, and all that kind of jazz because of the way that things are designed. Whatever, it slows it down, that kind of stuff. But if you understand where all those weaknesses are, now you know where you can move that energy to where you want it to go. It's all about guiding energy to where you want to go. It's how you actually use that energy in the most efficient manner. And so when it comes down to producing a free energy device, you need to know every possible loss that could be a potential drain on that system so that you can move that energy where you want it to go. And if you're capable of getting out more energy than you put in, which is something that's argued against in the laws of physics and such, and this is why all the debunkers out there mouthing off at everybody, because they believe themselves to be so incredibly intelligent that they just don't understand what it is that people like myself have been trying to say. You move this energy in the most efficient manner. You store this energy. You use capacitors as a buffer between your load. Number one, your batteries aren't going to get near as hot, if they get hot at all, as they would have otherwise if you're draining that directly off. If you know what's causing the lens effect, if you know what's causing eddy currents, then you can use those physics as well to your advantage. And it only becomes a loss in the system if you allow that energy to be dispersed out into the atmosphere. If you contain that energy all the way through the entire deal, what you started on this side, you're going to get on that side. And if you understand what's going on in this signal generator right here, the fact that I'm starting with 5 volts, and keep in mind, I'm not talking about amperage and I'm not talking about wattage. I do not care about amperage or wattage. I do not care at all. Voltage is pressure, and voltage is what gets work done. And if you understand how to take that energy off of that without putting that thing under serious stress, you won't burn that signal generator up by trying to draw too much from that signal generator, more than it's capable of handling. You try to draw too much from that, you'll burn it up. If you push too much back into it, you'll burn it up. I already did that. I burnt one up, and they're not cheap, so I don't want to do that no more. So taking that energy off of there, using it in the standard fashion to run your test and all that kind of stuff, and not abusing it, that signal generator will last for a long period of time, as long as it doesn't reach its thermal breakdown point. The same thing with your generators, the same thing with your internal combustion engines and all that. If you move that energy away from that system and you don't allow it to reach its thermal breakdown, it will not fail. You find the weakest part in any system, that is the full strength of that system, because that weakest part, the numbers on the weakest part, which are going to reach the thermal breakdown, will tell you when that engine, that electronic, will fail. And if you can keep that one specific part cool, then all the rest of them, which have a higher thermal breakdown, are perfectly safe as long as that one weakest spot is cool. And this is basically understanding mechanics and physics and how energy actually travels and such. So when you're building your alternative energy devices, find the weakest spot in the entire system and work your way out from there. Because the weakest spot is going to be where it will fail, where it draws too much energy and then finally shuts itself down. If you're demanding too much from that generator, it will fail. That's why you look on any generator out there, if it says it's got like 6,000 watts peak, but normal run time maybe only 4,500 watts, if it's under a heavy load or whatever that it's capable of doing. If you have a generator that says you have access to 6,000 watts, and you're not getting the full 6,000 watts out of that generator, then you're abusing that generator and you're not using that electricity in its maximum efficiency. You move that energy completely away from that generator. You allow that generator to do its job without trying to be asked too much of. That generator will not get hot. It will use, if it's a gasoline engine, it will use less fuel, and you will get the maximum amount of power that that generator is capable of doing out the other side. And you store that energy, you use a buffer system to keep that energy away from that generator, and you will make it super efficient. This is what I hope to show you by this series with the how far we can push efficiency. Now right now I'm setting at 7.75 volts on my output of the bridge rectifier while all of this stuff is running. While everything's going on here, you got to calculate when it comes out of that wire over there, out the output of the signal generator, pulsing 600 hertz square wave. You got to calculate that capacitor. You got to calculate that transformer. You got to calculate those AC capacitors. You got to calculate the bridge rectifier. You got to calculate those capacitors over there, both large and small. You got to calculate the circuitry and the entire load that these two car audio amplifier capacitors, 500,000 microfarad. You got to calculate those. You even got to calculate the doggone voltmeter while it's in series, because there's some sort of resistance as it's going through there while it's trying to tell you the voltage on there. You got to calculate the doggone boost converter circuit. It starts up at 3 volts, whatever the milliamp range that it'll actually start. You got to calculate that in. You got to calculate that blinking LED. You got to calculate the resistance of this 7.2 volt nickel cadmium battery. You got to calculate the resistance of this 9 volt nickel metal hydride battery, and that 9 volt nickel metal hydride battery all run in series with that one specific capacitor on the right. And so all of those calculations, all of what would have been a loss in this system, the way that this is being ran, we're still maintaining 7.75 volt surplus off of this deal. Everything that's not on these right here is voltage that's being used by any one of those loads there, coming off of that DDS signal generator output from the initial 5 volt output that is coming off that surge protector and that USB charger. So without running on AC current, you can connect that to a 5 volt source. That same DDS signal generator will run off of a 5 volt battery pack. Do all the calculations of what's going on right here. Look at all the voltages, factor in all the losses, and determine your efficiency from that point there. And so if you get even only at 80% efficiency, and you throw in any kind of outside deal such as a solar panel, wind turbine, or whatever, and then you run that thing in the same exact fashion, or you run simultaneous circuits pushing out multiple high voltage sources, charging up this entire system, while this thing's under load from when I started, it continued to rise. The voltage continued to rise. We're down at 5.30 right now. We still haven't got down to where its actual balance is, but you can see throughout this entire video that my 7.75 volts, my 5.30 aren't dropping rapidly. They're slowly going down, and it will finally reach its entire balance from everything that's connected to the circuit so far. Everything's connected to the system. That will finally get down to about 7, I'm going to say 7.04, but normally it stays about 7.06. It'll finally get down to about 7.06, and then it will fluctuate up and down between 7.10 and 7.06. But conservatively, I just go ahead and drop it all the way down to 7.04. All of these loads, every bit of resistance that's on here, and then it finds its balance. If those numbers are higher than those numbers up there, then you got some efficiency, because everything that's showing on these right here right now are surplus. Now if I put that under a direct load, I can drain, if I put like electric motor onto there, I can drain it down really good, real fast. So with that said, as long as I keep that energy flowing in there faster than I can drain it off in the form of high voltage pressure, keep those balloons full at all times, while at the same time running energy through these rechargeable batteries. Basically everything that's in between this and any of the loads are acting as a buffer between that output that is not demanding more from that output than that output's actually capable of achieving. They say that those signal generators will produce 9 volts while it's not under load output. So if you want to look up that particular model, it don't have a model number on it. It's just a DDS signal generator bought off of eBay for like, I don't know, 60 bucks or somewhere. Either way, all this time I've been talking, you can see that circuit's still, the little blinking LED still going on. The batteries are still connected. These are the voltages on there. And if you like this video and this type of research, give me a thumbs up and share this with people, because I'm working on something right now that when I get it achieved, you're going to be really happy. I guarantee you that. Anyway, peace and love, everybody. Take care.